Thank you all for getting here early. So yeah, I'm giving a talk about quantum resistant rollups. Before getting into the quantum resistance aspect, since I think rollups are still a kind of fresh topic for a lot of Bitcoiners, I figured I'd give a brief intro to validity rollups. But first, a detour into rollup ontology, just because I think once you take a peer into the rollups world a little bit, you'll get hit with a lot of terminology. So I just want to maybe quickly clarify that for people. So what is a rollup, just like in general? No, not those kinds of rollups. A rollup is a blockchain that stores enough data inside of the blocks of a parent blockchain to compute its current canonical state. And what this gives you in terms of its properties are that rollup blockchains have data availability that is equivalent to the parent chain because its state data is stored inside of parent chain blocks. Its data is as available as its parent chain's data. And it also has double spend resistance that is equivalent to the parent chain. So whenever a rollup block gets confirmed inside of the parent chain block, you need to actually reorganize the parent chain block in order to reorganize the rollup block as well. This kind of differentiates rollups from like side chains, which can typically be independently reorganized separate from the parent blockchain. So there are two kind of high-level categories of rollups. There are like quote-unquote sovereign rollups, and then there are smart contract rollups. The primary difference being that sovereign rollups are typically just somebody running a full node somewhere. Maybe that full node is like running in block producer mode, and then they just stuff blocks inside of the blocks of some parent blockchain, and they're just kind of using that parent blockchain for data availability and double spend resistance. Smart contract rollups actually have a kind of smart contract connection on the parent chain. So they're typically doing some kind of checkpointing into a specific contract, and then you can put assets into that smart contract and move the assets back and forth between the rollup chain and the parent chain. But let's take a closer look at this. So within the kind of smart contract rollup paradigm, you typically have two major categories of rollups: optimistic rollups and validity rollups. And so we're going to be talking about validity rollups specifically today. So what is a validity rollup then? A validity rollup, it has a trustless bridge using this smart contract on the parent chain between the rollup chain and the parent chain that is secured by a validity proof verification smart contract. What that means in particular is like for every kind of checkpoint that the rollup is putting on the parent chain, it is giving that checkpoint to the specific smart contract, and then it's also providing this cryptographic validity proof to the smart contract to prove that the checkpoint and all of the rollup transactions in the checkpoint are valid. And with that, users can receive asset transfers on the rollup chain even if they are offline and even if they have never used the rollup chain before. So the same way that a new user of Bitcoin can just spin up a Bitcoin wallet, give their counterparty an address, and receive coins without having any kind of pre-existing relationship, a rollup is just a blockchain. So you can kind of treat it in your mental model as like it's a blockchain. The user experience is just like using any other blockchain. Thanks to the fact that all of the transactions are validity proven, only the current owner of an asset can actually transfer or withdraw the asset. And typically, users can also withdraw their assets from the rollup chain to the parent chain, even if the operator of the rollup is uncooperative, meaning that the users have this ability to unilaterally exit the chain. And the way that they typically do this is they would just go to that smart contract that's on layer 1 or the parent chain, and they would supply a cryptographic proof to that chain, to that smart contract, that they own these assets in the rollup and they want to get them out. and the smart contract has the ability to like verify that proof and give the user their funds, even if the rollup chain itself is halted. And then finally, you get this nice capability that transactions on the rollup can be compressed to strip out data that is made redundant by the validity proofs. And this enables higher throughput, which we'll get into later and kind of explain exactly how that works. So typical kind of flow is like, if the rollup is, let's say, built on Bitcoin, Alice would kind of send BTC to a rollup deposit address on L1. The rollup software would detect the deposit and credit Alice's address on the rollup. Alice would like send her BTC to Bob. Now, let's say Bob wants to get his BTC back out onto the main chain. So he sends his BTC to a withdrawal contract on the rollup side. The rollup block producer would prove the validity of Alice and Bob's transactions and then submit a checkpoint to the smart contract on layer 1. And then the smart contract would kind of would like spit the BTC out to Bob's specified withdrawal address. And this all happens somewhat autonomously thanks to the smart contract and the fact that all of these operations are being cryptographically proven and verified. So yeah, at a high level, this is how you can kind of visualize it. You've got two blockchains like running in parallel, and then the one on top is the rollup chain. It has this two-way bridge, so you can transfer assets back and forth between the parent chain, in this case Bitcoin, and the rollup chain. And then every so often, you'll get a block or a batch of blocks that gets put onto the parent chain along with a cryptographic validity proof that those batches are actually valid. Of course, if that proof resolves to false, it's not a valid proof, then the smart contract on layer 1 is going to reject it and just wait for a valid batch and proof to be provided before it goes to the next state transition. So yeah, at a high level, the features that you get with a validity rollup are that there are no interactivity or monitoring requirements for users. Receiving is not limited by any kind of like channel capacity with a sender. Like I said, the UX is just like any other blockchain, not a channel-based system. You have high but not unlimited throughput, and we'll kind of get into the throughput numbers a little bit later. But you can kind of get this minimum best case of 35x transactions per second compared to transactions on layer 1. And by minimum best case, what I mean is like you can compress transactions into a really small size, but then you can also do interesting things like cut through with a bunch of those transactions. So if you have a bunch of transactions that you can do a cut through for, you can get even higher throughput. But in the worst case scenario where you can't do any kind of cut through, but you have a full block of these transactions, you still get like 35 times the transactions per second than what you can get on Bitcoin layer 1 today. You can also have custom execution environments. So I think this is really interesting because layer 1 is just accepting a validity proof. That validity proof could be for a generic, what's called a ZKVM, which enables you to have any kind of program on the other side of that. Some ZKVMs are like tailored towards specific languages, so a lot of the ones that you see today are specifically for Rust, but you can basically prove any Rust program. And so you could have a validity rollup that like looks exactly like Bitcoin, or one that looks like Liquid, or one that looks like Rootstock, or one that looks like Zcash. Like if you have a kind of generic verifier on layer 1, the execution environment of the rollup can be like whatever you want, really. It's low cost for the parent chain nodes to verify because these cryptographic validity proofs verify they're not too much slower to verify than just an ECC signature, and they can be trustless. So which means that the funds cannot be frozen or stolen because everything is being cryptographically verified. Perhaps the most notable downside is that, at least today, they're relatively expensive to operate. Producing these cryptographically validity proofs can be quite expensive, but the costs are rapidly dropping just because people are really excited about this, pouring a lot of money into it, and like optimizing the hell out of these things. So that brings us to the quantum resistant rollups. And so what makes a rollup quantum resistant is that you can use like any post-quantum signature algorithm or proof to spend rollup coins. So if you're like a user of the system, the rollup could actually just implement natively a post-quantum signature algorithm, or even just say like, hey, provide a post-quantum proof, like a Stark, in order to spend your funds on the rollup. Like that can be the rule for like how you spend funds on the rollup. And then the second kind of aspect that's important to be post-quantum is the actual proof system for the proof that is going on layer one. And so in that case, depending on what your layer one supports in terms of the proof system, you could use any kind of post-quantum proof system, post-quantum Stark, or even there are some post-quantum Snark varieties that have been introduced. And that's what you would actually put in your checkpoint transaction that goes on layer one, and that layer one is verifying. And there have been some proof of concepts of this already, showing how you can build like a Stark verifier in script using some additional opcodes that are not currently active on Bitcoin, which we'll get into later as well. So this is how, say, a quantum-resistant rollup would compare to some of the other post-quantum ways of like using Bitcoin. So we have a couple of these post-quantum signature algorithms which have been proposed for implementation directly in layer one. These are the ones that BIP 360 talks about, SLH DSA and ML DSA. And we can see that like the transaction sizes are quite stark in difference between the SLH DSA, ML DSA, and then the kind of like Stark or cryptographic proof-based systems, and it's not kind of a direct comparison because you can see this like little proof divided by n thing, and it's because the idea with these BitZip and QR rollup proposals, and I'm giving a talk about BitZip later if you want more context on that, but the idea is that you can, as I mentioned earlier, with rollups and also with BitZip, you can strip out a lot of information in the transaction that's made redundant by the cryptographic proof itself, primarily the witness, and that gets you transactions that can be as small as like 76 bytes. And in some cases, if you want an account-based system, it can get down even smaller. But in this case, the example is like using 1 in, 2 out UTXO-based transactions. And then you amortize the cost of the cryptographic validity proof over all of those transactions. So that's where you get this like proof divided by n, where n is the number of post-quantum transactions that you have in that block. But if your proof is like 100,000 bytes, and your the raw transaction data itself that you're putting on chain is 76 bytes, then with a quantum resistant rollup, you could get 83.3 transactions per second, which is more than 40 times what your biggest post-quantum signature on layer one would be. And then on the future-proof side of things, what I mean by future-proof is like if we implemented the first two post-quantum signature algorithms directly on Bitcoin layer one, and then something, some tech advancement came along that made them better, or maybe there was a bug that was found in the implementation or something like that. Like we would actually have to do a consensus change in order to adopt the new technology or fix the bug. Whereas with rollups, one of the things I think is interesting about rollups is that different rollups can implement different things. And if you have a like generic enough verifier on layer 1, you could have this free experimentation at the rollup layer where different rollups kind of optimize for different things or are taking different kinds of trade-offs. Like maybe some go with the lattice-based stuff, some go with the hash-based stuff. And if you find issues in one system, you can kind of fix them in another system, and you don't need to make any changes directly to layer 1, unless the proofs that you're actually putting on layer 1 have bugs. But if those are solid and you're just kind of doing experiments at the rollup layer and one of those has a problem, then you can kind of just fix that by creating a new rollup with the fix implemented. So it has an aspect of future proof to it that the other proposals do not, that I think is interesting. And then there's one more that I added here, which is Shielded CSV, which I think has a lot in common with the rollup proposals, but with this, you can actually get transactions size, like the size of data that goes on layer 1, down to as small as like 64 bytes per transaction. But you also, which increases your transactions per second to about 104 transactions per second. It also provides really great privacy by default. You kind of get privacy strong privacy for free. And it also has this nice like future-proof aspect to it where, if something is wrong with your signature algorithm that you're using for sending transactions, or you just find a better, maybe more space efficient or whatever you're optimizing for kind of system, you can just deploy another implementation of Shielded CSV and with those improvements. So that's how I would compare the different kind of proposals that are floating around. Again, I'm going to be giving a presentation about BitZip later, so come back for that if you're interested in hearing about that. And so some action items that I would leave for the Bitcoin community if this sounds interesting to you. So in order to kind of get all of these benefits that I'm talking about with quantum resistant rollups, we need to disable key path spends. For example, BIP360, I think, proposes to do this. We have to have some kind of ability to verify zero-knowledge proofs or at least post-quantum validity proofs on Bitcoin layer 1. And one way to do that is by having opcat and opmol. You put those together and you can get pretty space-efficient validity proof verification scripts on Bitcoin layer 1. And you could also have something like op proof verify, which would be an opcode on Bitcoin layer 1 that's specifically tailored to verifying a specific kind of proof system. That opens questions of like which proof system, and that would probably be endlessly bike sheddable. So I tend to prefer the more generic kind of approach of like opcat and opmol, where people kind of have the freedom to build what kind of verifier they want, but it's ultimately up to the community to decide what to do there. And then some things that would be like very nice to have, but not strictly necessary, would be like big integer arithmetic specifically, and optx or some other kind of like space efficient recursive covenant opcodes, so that we don't have to do unholy things in script to make recursive covenants work with opcat. So yeah, these are some of the references that I pulled from to come up with the numbers that I presented today. I'm happy to kind of dig into those if anyone has questions. And yeah, I want to leave some time for questions if anyone has questions.
Okay, so I wonder if this proposal is sort of putting the cart before the horse, if you will, because you have to presumably peg in Bitcoin to some on-chain address that's then used in this off-chain blockchain. So how do we secure the on-chain address to be quantum resistant?
Yeah, so first, like I said, we have to disable keypath spends. So that way we restrict spending from that address to the script path. And then the script would be this validity proof verifier script. So that in order to spend from the address, you have to supply a validity proof that the program that is being proven is being satisfied. And this program is like the consensus rules of the rollup. And so as long as you can provide a validity proof that proves that that's valid and then proves other conditions of the script are being satisfied, like for example, if the script is holding 10 Bitcoin and you're trying to withdraw 5 Bitcoin from the rollup, it would be sensible, let's say, to have also an additional requirement that you send the change back to the address. So there's no signatures. It's just a proof. It's just a cryptographic proof.
In your comparison, you had shielded CSV sneak in at the last point.
Yep.
Could you perhaps, in a couple sentences, put it in the context of rollups? How does it compare or not compare? Is it also quantum safe? And what are the other trade-offs? Like, why would you put it in this table, but why didn't it fit into your talk, basically?
Yeah, that's a really good question. Well, I was invited to talk about quantum-resistant rollups primarily, but I didn't want to leave it out because it is, I think, a valid proposal or solution to how we could help make Bitcoin post-quantum. And so the idea with shielded CSV is similarly to a rollup, you need some kind of bridge to get Bitcoin into this system where transactions are primarily happening off-chain. But the idea is that users will transfer their BTC into this system, and then they receive their shielded CSV node will detect that they have received a deposit, and then they are able to create a cryptographic proof that they own these coins, and they can transfer them to somebody else. But instead of broadcasting that transaction to a peer-to-peer network and then all of that transaction data eventually goes on chain, instead what they do is they produce a nullifier to nullify the coin, and they put that on chain, and then they send a bundle of data off chain to the recipient that says, hey, I just spent this coin, here's the nullifier to prove that it's I haven't double spent it, it's on layer 1, and I'm giving you a cryptographic validity proof that the coin that I'm giving you corresponds to that nullifier and that coin hasn't been double spent. And so the bulk of the data of the transaction is actually transferred off-chain. So that 64 bytes that I talk about that goes on-chain, this is locked. The 64 bytes that I say goes on-chain is just that nullifier. The rest of the transaction data gets transferred off-chain. And the way that it can be post-quantum is that the encryption that you're using to encrypt the transaction details to the recipient can use post-quantum cryptography, and the proving system that you use to produce the cryptographic validity proofs that proves that your transaction is valid and the coins haven't been double spent and everything, that can also be post-quantum. And yeah, one of the nice things is that Bitcoin itself is mostly blind to everything that's happening. All it sees is the Bitcoin that goes into the system and out of the system, and then it has to keep track of these nullifiers. Well, Bitcoin doesn't keep track of the nullifiers, but you store the nullifiers in a Taproot witness or something.
One more question. Hey, so as somebody who works for a mining company, I'm constantly thinking like, how does this benefit miners? And if it does benefit miners, that makes it easier to sell because it's incentive compatible with miners, right? And so I kind of want to get your feeling on BitZip versus rollups versus like in terms of how they benefit miners.
Yeah. Well, BitZip, and I'll talk more about it in my upcoming talk. But BitZip BitZip transactions basically just look like Bitcoin transactions. There could maybe be scope for like expanding the kinds of things that BitZip transactions can do compared to normal Bitcoin script. That's maybe a community decision, not something I can say like is a for sure guaranteed outcome. But rollup transactions tend to be, again, it also kind of depends on what kind of verifier you enable on Bitcoin layer 1. But certainly the kinds of rollups that people today are building are like more expressive, and so you can just do more things with your Bitcoin. And I think it's nothing that I can guarantee, right? But like I think it's likely that if people can do more things with their Bitcoin, you have more use cases that's going to generate more fees for miners. And all else being equal. And so that's maybe one way, but I think ultimately it just depends on how people end up using these things. I don't know, maybe you get a kind of induced demand effect due to the fact that you can fit more transactions on chain, but yeah, it just depends on how users end up behaving and using these things.
So increasing utility and inducing demand, like having more supply of transaction TPS, right? Like all that's could help concentrate fees into the hands of miners. I just like the validity rollups. I would imagine like probably wouldn't share as much in fees with because like they operate in their own system, right?
Yeah, so there are kind of fees happening at two different levels. One is like the block producers on the validity rollup. In some cases, it's a central party or like a federation, but there are also these things called based rollups where the layer 1 miners themselves are actually doing the block production on the rollup. And so in that case, the fees from layer 1 and the fees from layer 2 would kind of like both go to miners. But even in the case where you have a single party or a federation or something like that, a separate set of block producers for the rollup, they have to pay transaction fees to put the rollup data on chain and to pay for the operation of the script. So, and of course, if there are multiple rollups, then they're kind of bidding against each other, and of course, all other users of Bitcoin to like get their transactions included. So it's not like they're totally siphoning fees away from the miners either.
Good. That's a good mental model. Thank you.